Okay, we're going to take a look at an exponential question. And I'm also going to do a second part of this question where we have to use log to isolate for a variable. Okay, so we have an insect colony and they have a current population of 50 insects. And this population doubles every 3 days. So that's going to be important, so I'm going to underline that with another color. And we want to know what is the population after 12 days. So 12 days and 3 days, these both deal with time. So I know these are both going to deal with our x value. Okay? We're using the formula y equals a times b to the exponent x. Okay? Y is our future value, a is our initial value, b is our doubling factor, or our, maybe not doubling, but in this case it doubles. It's our growth factor, I guess you can say, or our decay factor. And x is our total time over time for the growth or decay to occur. Okay, so let's take a look at what we have here. I know that we have a current population of 50 insects, so I'm going to plug that in for A in a moment. Okay, it also doubles, so the doubling tells me that my B value is 2. Okay, that's my growth rate, or my growth factor rather. Okay, and then x is total time over time it takes for one doubling to occur. So total time is a 12-day period, and it takes 3 days for our population to double. And I can reduce that to just 4. Okay, what we don't know here is our y value. That's what we're looking for. We're looking for the future population after 12 days have happened. Okay, so let's go ahead and just use this formula here and plug in what we know. We know that A is 50, B is 2, and X is 4. Okay, I'm going to make sure that I follow BEDMAS here. So rather than doing 50 times 2, I'm going to do 2 to the exponent 4 first, because that's how BEDMAS works. Okay, so 50 is going to stay as it is, and then we're going to do 2 to the exponent 4, which is 16. Okay, then we can just calculate this out quickly. 50 times 16 is 800. Okay, and then we're going to do a nice little therefore sentence. So therefore, there will be 800 insects after 12 days. Okay, so that's a pretty straightforward question. You'll probably see a question like this that just kind of tests knowledge, basic knowledge of how to pick something out from a question and plug it into the formula. Now this one's a little bit more difficult, just because it deals with solving for an exponent. So this insect colony is actually full of giant mutant intelligent insects. They plot that they can overtake the Earth when their population has reached, 1 billion. When will we meet our doom? Or in other words, when does the population actually reach 1 billion? Okay, so we have some of the same variables as our first question. Our initial population is still going to be 50. We are still doubling. Okay, so our B value is still 2. This time we know our Y value is 1 billion, so that's 9 zeros. Okay, and there's part of X that we know, but there's part of X that we don't know. We don't know the total time that it's going to take for the population to reach 1 billion. However, we do know that it doubles every 3 days. Okay, so let's plug in what we know into our formula. 1 billion equals an initial population of 50 times 2 to the exponent t over 3. Okay, that's y, a, b, and x that we just plugged in there. So the first thing that we need to do here is get the base and the exponent by themselves. So I want the 2 and the t over 3 to be isolated on one side alone. That means that I need to do something with this 50 here. And because 50 is being multiplied by 2 to the exponent t over 3, I'm going to do the opposite of that, which is divide. Okay, so these 50s are going to cancel, and I'm going to be left with 20 million on this side over here. Okay, so we have a base and an exponent isolated on one side. This is where our logarithms come in. What I'm going to do is I'm going to take the log of both sides, and we learned that when we use log, we actually get to take this exponent and use the parachute rule. We get to parachute it down in front as a multiplication. So here's what we end up with. We end up with the log of 20 million equals t over 3 times the log of 2. Okay, you can see how this is great because now we have the t down somewhere where we can actually use it, and we can get rid of that log of 2 by just dividing it out because it's being multiplied right now. Okay, I'm not going to even evaluate yet. Don't get calculator happy. We don't want to start with that just yet until we've got this kind of isolated out a little bit more. Okay, so look, this is what we have now. Okay, so here's what we've got. Now I can use my calculator. Now that we've cleaned this all up and we're not going to get confused or anything like that. So I'm going to type into my calculator log of 20 million over the log of 2. And I'm going to leave quite a few decimals here just so we can be a little bit more precise. I got 24.2534966. Okay. And the only thing that I have left to do at this point is to get this t by itself. So right now I'm dividing by 3. So I'm just going to multiply both sides by 3. Okay, and again, I left that value of the log of 20 million over the log of 2 right in my calculator. So what I'm going to do is I'm just going to go times 3. And we end up with 72.76. Okay, so what does this mean in terms of our question? Well, the question asks us, when will we meet our doom? So when does the population of the insects reach 1 billion? So in about 72 and 3/4 of a day. Okay, so therefore the insects will reach a population of 1 billion in about 72 days. We should probably be ready with heavy artillery at around 70, 71 days just to be safe.